Welcome to the Mind Factory, a channel where we reproduce the latest results in artificial intelligence, deep learning, and robotics. In this video, I'm going to provide a general explanation of what imitation learning is and how it works. This is a supplementary to my video series where we reproduce the paper entitled Learning Fine-Grained Bimanual Manipulation with Low-Cost Hardware. Okay, let's get into it. So to explain behavioral cloning, first let's create a little robot here. Okay, here's our robot. And this robot has, 3 joints. And the joints, have orientations, they have positions. So, this one is 9 o'clock, this one's 12 o'clock. Let's just imagine, this is simple, this one's like 5 o'clock or what have you. And imagine, we've got a task that we want to do. So imagine we want to, pick up a cup, right? So here's our cup. Here's our cup. Okay. One way we could do this would be by just writing a series of actions, which would be different joint positions of the robot, and just playing them back. So imagine, we had a table, right? And so we've got this big table here, and we have this list of actions. Action 0, action 1, action 2, action 3, ... all the way down to action n. Okay. So we would just simply replay this set of actions. We would put the cup in a very specific position, and then we would replay the actions, and then that would cause the robot to exactly reach out and pick up the cup. Okay. But as you can tell, that's not really a great way of doing it. It's going to be very fragile. I mean, you can actually get a lot done that way, but it's going to be it's not going to be very robust. So another way we could do this is we could say install a camera. So we could have a camera. So here's our camera, and it's looking at this scene, and it's generating an image over here. So we've got this image over here of what's going on, and in that image, you've got a cup, and we can see where the cup is in the scene. And now, theoretically, we could use this to figure out what the action should be, right? And in addition to this, imagine we also had, under here, the joint positions. So we just had that. We had just these 3 things as the joint positions. Okay. And then you could imagine, a trajectory of the robot interacting with this cup. You can imagine the trajectory of this could go off into time. So we would have a stack of images, like lots of images in time. Right. And that would be an accurate representation of the state and trajectory of the robot. All right, so what we're going to do is we're going to call this the state. So we're going to call this the state of the system. So we're going to call this, for now, we're going to call this the state. And imagine, if you had a lookup table that for every different position that the cup could be in, you had you had the correct settings for what you should do with a robot arm. Okay, so the correct next thing for every position the cup could be in, and for every position the robot arm could be in, you had like a lookup table which told you which action to take next. So that would look like this, right? We would have the state over here, and there would be state 0, do this action, state 1, do it that action, and so on, right? And we would have like just tons and tons of states in this table. Now, obviously, that's not really going to work because the different pixels in this image, all the different places the cup could be, it would be a gigantic table that you could never fit into a computer memory. But what we might do instead is we might make an approximation, right? We'd do what a mathematician loves to do, which is make an approximation of this. So one way we could do an approximation is we could actually turn this table into a function which takes in the state and also has a set of parameters. So this is a tunable function, and outputs an action, right? Outputs the action. And just for the moment, instead of calling this function f, okay, we're going to call this function pi. And we're going to refer to this function hereafter as the policy. now the question just becomes, well, okay, well, how do I figure out what the values of what the right parameters are? And if you've done any sort of neural networks, the next step's fairly obvious. What you would do is you would build up a data set, which looks exactly like this, a set of a big, gigantic table where a bunch of trajectories of the robot doing this specific task, picking up the cup and doing whatever you wanted to do with it, and you would call this. Let's call this for the moment the approximate action that I wanted to take, and let's call these guys the just the normal action I want to take. And so then what I would do is I would define a loss function. So I'd make a loss function, and I would minimize that because it's a loss function. With respect, I would be looking for the parameters of theta that minimize this such that pi state theta minus the actual action, because if you remember, pi state theta equals, as we can see, the approximate action minus the actual action. That's what I would optimize. Right? I would try to find parameters of theta such that this was as small as possible. Because if this a hat action minus the action that I'm going to take equals 0, then that means this policy is going to exactly reproduce what's in the data set. And the beauty of parameterizing it is even when I see something that's not in the data set, if I saw a state with the cup that was just a little bit closer to this, it was a little bit different, but pretty close to this position, it would produce a very similar type of action to that. So now I don't need a lookup table with every state in it. I just need to get an approximation of it based on some data. And that is essentially the idea behind behavioral cloning or imitation learning. It's essentially just supervised learning, but done on a robot. Okay, hope that's helpful.
Okay, so I hope you found that useful. If you're interested in seeing how this could actually be applied, then you might want to check out my video series where I reproduce the results from a paper called Learning Fine-Grained Bimanual Manipulation Using Low-Cost Hardware. In this paper, they actually use imitation learning to do some tasks on a robotic arm. If you find this content interesting and you're generally liking it, please hit the like button. If you want to see more, press the subscribe button, and we'll catch you in the next one.